This is problem 2 for homework 6.1 and 6.2. Given a 3x3 matrix A, find H in the matrix A such that A is diagonalizable. A is diagonalizable if and only if A has n linearly independent eigenvectors, if A matrix is n by n in series. Since A is a triangular matrix with diagonal element 2, 4, and 2. So A has the eigenvalue 4 with multiplicity of 1 and the eigenvalue 2 with multiplicity of 2. The repeated eigenvalue 2 should have its eigenspace whose dimension is equal to 2, which means it's spanned by 2 vectors. This requirement allows a total of 3 linearly independent eigenvectors. When we try to solve for A minus 2 times identity matrix, we will have this 3x3 matrix, and then we do the Gaussian elimination. We will get this 3x3 matrix. Our goal is to get 2 free variables. We know x1 can be free, and if we have 2 rows of zeros, which means 3 minus h is equal to 0, then we should have 2 free variables, so that h has to be equal to 3. Now, let's diagonalize matrix A with knowing h is equal to 3. Eigenvalue matrix will be our D matrix, so its diagonal elements should be the eigenvalues. And we also need to find the eigenvectors for these 2 distinct eigenvalues. The eigenvalues are 2 and 4. So for eigenvalue is equal to 2, we will do A minus 2i, and the augmented part will be 0 vector. It's going to be this matrix, and then we do the Gaussian elimination, and eventually we will have this. So according to this augmented matrix, we know x1 and x2 can be free, and x3 is dependent of x2. We can do x1 is equal to s, x2 is equal to t, and x3 is equal to negative 2 times t over 3. Thus, the basis for this eigenspace is built by these 2 vectors, 1, 0, 0, and 0, 1, negative 2 over 3. Okay, then we will do eigenvalues for 4. So A minus 4 times the identity matrix, where the augmented part is equal to 0 vector. We will have this 4x3 matrix. Then we will do the Gaussian elimination to reduce it, and by that reduced REF, we will find x1 and x2. x1 can be free, and x2 depends on the value of x1. So x1 is equal to s, x2 is equal to s, and x3 should be equal to 0. So the basis for the eigenspace of eigenvalue of is equal to 4 is equal to 1, 1, 0 vector. Thus, if we combine the matrix P, D, and P inverse, we can write matrix A is the product of P, D, P inverse equal to this.